In this video, we are going to see a numerical example of linear load flow. Before going ahead, I would like to point out some of the corrections in the previous video. In this expression, I bus equal to Y bus V bus. The bus I bus basically represent current injected into the bus, but we are writing expression for load currents, and that load current should be appearing in I bus matrix with a negative sign because I bus represents current injected, but load is instead taking away from the bus the current. So that is the reason why when we write the load equation, that should be equal to negative of I bus. So the correction should happen here. I'm writing it in a different color. So when we write I bus and when we treat I2, I3 and so on up to IN as a load currents, then we put negative signs over there. So that should be the thing. So here it will impact in the derivation is here. Yes, so when we write in as yn1v1 and ynnvn, they should appear with a negative sign. And here it will be a negative sign. So because of that, when we take that on the right hand side, that becomes plus and that becomes plus over here. That is the correction. So rest of the other things will remain as it is since we are representing this quantity as A dash and that as C dash. So the further derivation remains unchanged. Only the sign convention will be different. So that is one correction. Another correction is in this. So we derived or linearized this 1 by v non-linear term as 1 by v naught plus 1 by v naught multiplied by 2 minus v by v naught. And when we take conjugate on both sides, so here it should be conjugate here and here also conjugate in the v naught dash. But the thing is, v naught represents nominal voltage. And usually we take nominal voltage as a reference quantity. So whatever its amplitude is, we take its angle to be equal to 0. So since angle is 0, this is same as not conjugate. So even if we take conjugate or not, that should not matter for a reference quantity or the base quantity. So base is always a real value, a real quantity. It does not have any imaginary part or angle part. So that is the reason why even if we take V naught or V naught conjugate anywhere in the equation, that simply means it is the magnitude of V naught. Angle is 0. So here going ahead, we have these equations where we have V naught and V naught star. So both are can be treated as a equal thing. That is another comment. And one more comment in this is we are writing the equation of current, the equation of load current as Ik equal to Sk conjugate by Vk conjugate. So here we are assuming a per unit equation. So in per unit, there is no term of 3 or root 3 here. So if it is a three-phase balance system and if Vk is represented as line-to-line RMS value, then the factor of root 3 should come there. If in case Vk is represented as a phase to ground voltage, then there should be a factor of 3 over there. And if in case it is a three-phase system, but we are doing per phase analysis, then there should not be any factor. So according to what quantities we are dealing, are we dealing with actual quantities? Are we dealing with a balanced system or per phase analysis? Depending upon that, the factor can change. But that is just a scalar factor. Other rest of the other concept and derivation remains the same. So these are some of the comments in the earlier video. Now in this video, we are going to see a numerical example and how we can incorporate this algorithm to solve a load flow in a single iteration. So let us take this example. Let us take this as a substation bus number 1 and a line connects to bus number 2. Bus number 2, some load is connected. So the load is 0.5 plus j 0.2. And another line connects to bus number 3. And the load at bus number 3 is 0.3 plus j 0.1. So all the quantities given here, these are per unit quantities. And let us assume that the load is a constant power load. So the S2 is this and S3 is that in per unit. So that is the thing. Now about line, let us assume that line 1 to 2 is overhead distribution line, and it is a short line, so it has only series impedance. So the impedance is given by 0.05 plus j 0.05. You can notice that X bar ratio is equal to 1, which is typically the case for any distribution line. X bar ratio is closer to 1. The line 2 to 3, let us assume that it is an underground cable. So since it is an underground cable, it has non-negligible shunt capacitance also. So the line can be represented as a pi model like this. So with respect to ground, there are shunt capacitances at sending end and receiving end, and there is a series impedance also. So the series impedance is, let us imagine that as zero point 0.1 plus j 0.1, and the shunt admittance that is given by j 0.2, j 0.2 on both the sides of the bisection. So this is the data given. Notice that this Z between 1 to, that is the Z impedance. It is not admittance. So this is Z 2 3 is this, and this Y shunt is J.2. So this is the admittance given to us. Now the first step here in the linear load flow algorithm, that we started with Y bus matrix. So we need to derive a Y bus matrix for this. Here we have 3 buses. So Y bus matrix, including substation bus, will contain 3 by 3 matrix. Okay. So what is Y12? So small y1 to 2, that represents the admittance of line 1 to 2. So it is just the reciprocal of 1 upon reciprocal of Z12. So if you do that, 1 upon 0.05 plus j 0.05, that turns out to be 10 minus j10. Similarly, we can derive y23 as 1 upon j23, which is 1 upon 0.1 plus j.1. That turns out to be 5 minus j5. And y shunt is already given. So now we can construct a Y bus matrix. So it will be a 3 by 3 matrix. So let us mark the 3 rows as just to make placeholders, and 3 columns like this. So let us first write the diagonal entries. Y11 is basically sum of admittances, whatever admittances are connected to bus number 1. Now the only admittance connected to bus 1 is this line Y12 admittance. So this is 10 minus J10. It is 10 minus J10. Now at bus number 2, we have line 1, 2, we have line 2, 3, as well as a shunt admittance J.2. So it is basically sum of all the 3. So it is this plus this plus this. So real part, when we add, that becomes 0.05 plus 0.1, that is 0.15, and imaginary, sorry, we need to add the admittances. Sorry. We need to add the admittance, not the impedance. The given data of the series is the impedances. So it is basically 10 minus J10 plus 5 minus J5 and plus this. So real part is 15, and imaginary part is 10 plus 5 is minus J15, and plus J.2. So that is I think 0.2. So that is 14.8. Okay. Now at 3, we have J.2 and 5 minus J5. So real part is 5 minus J, and we have 0.2 and 5. So that becomes 4.8. Okay. And in the off diagonal entries Y12, we have negative of the admittance. So that is minus 10 plus J10. Since it is symmetric matrix, so it is minus J10 plus J10 here also. Now 1, 3, there is no direct connection, so that entry will be 0, and 3, 1 is also 0. Now 2, 3, it is minus 5 plus J5, and similarly at 3, 2 position, minus 5 plus J5. So here we have constructed a Y bus matrix. So this first row corresponds to bus 1, second row corresponds to bus 2, third row corresponds to bus 3. Similarly, the columns correspond to respective buses. Now, next thing is to partition this into uh, four. So substation we separate out. So this is our y11. This we treat as y11. The this part we call it as y1n. Then this component we have treated that as yn1, and this remaining partition we call that as yn. So we constructed y bus and partitioned that. Next thing, let us go back in our algorithm. We need basically these entries, this A dash, B, and C dash matrices. So what is A dash, B dash, C matrices, C dash matrices? These are coming from here. So for that, yn1 we just obtained, yn we just obtained. Let us assume that V1 is basically substation bus voltage. That is same as nominal voltage. So that V1, just a minute. Yeah. So substation bus voltage, let us assume that say it to be same as nominal voltage, which is equal to 1 angle 0, which is our reference. Okay. So what data we have now? We have yn1, we have v1, we have yn. Now we need to derive A, B, and C matrices, and from there we will do further calculation. What is A matrix? A matrix is this one. So A matrix is consisting of SP terms, V0 is 1, so we can ignore that quantity. The SI component, which is basically corresponding to the power corresponding to constant current type of loads. In our example, there is no constant current type of load. So SI, all these components will be equal to 0. Similarly, in the C matrix, these components, which are basically representing SZ, constant impedance part, that is also absent in our example. So C matrix is 0. So we have only A matrix and B matrix. A matrix now simplifies to simply a column matrix of size starting from bus number 2 to bus number 3. 3 is the last bus. So we have 2 S2 star and 2 S3 star. So A matrix, let us write that in our case. So A matrix in our case is 2S2 conjugate and 2S3 conjugate. That is equal to, so S2 we have here, which is 0.5 plus J0.2, and 0.5 plus J0.2 conjugate, and S3 we have as 0.3 plus J0.1 conjugate. So you can solve it. It is 1 minus J0.4, that is 0.6 minus J0.2, that is the A matrix. B matrix, let us derive that. So B matrix is 1 upon V naught square, that is 1. Here, remember that there is a negative sign here, and it is the diagonal. The S2 and S3 conjugate are in a diagonal, and outside there is a minus sign. So let me write that. So outside there is a minus sign, and here we have a diagonal matrix S2 conjugate and S3 conjugate. So that basically denotes this one. So it is 0.5 plus J0.2 conjugate, and 0.3 plus J0.1 conjugate. And if you solve it, it is minus 0.5 and plus J0.2, 0, 0, and that side we have minus 0.3 plus 0. 0.1. So that is the B matrix. And as we have seen, C matrix is 0 because we don't have terms corresponding to constant impedance power. Okay, that is fine. Now we have to derive a dash matrix. A dash, what is that? A dash is A plus Y and 1 times V1. Now since V1 is just 1 per unit, so it is simply A plus Y and 1. So A dash is equal to A matrix 1 plus 5. So I'm just repeating A matrix here. In that we have to add Y and 1. Y and 1 is this minus 10 plus J10 and 0. So now the A dash becomes this. Okay. And B dash. B dash, there is no B dash as such. So we have B only, and C dash we need to derive. C dash is same as C plus Y N N. So since C is 0 in our case, we have C dash same as Y N N. So let us write that C dash same as Y N N. So B is same as B, and C dash is same as the Y N N matrix, which was written in earlier slide. So this is 15 minus J 14.8. 15 minus J 14.8, then minus 5 plus J 5, and 5 minus J 4.8. So now we have A dash, B, and C dash matrix. Now what we need next thing is their real and imaginary parts. So let us write that. So let us split the matrices in their real part and imaginary parts. So A dash matrix real is 9 and minus, sorry, yeah, minus 9 and 0.6. Then A dash matrix imaginary part is 9.6 minus 0.2. Then B matrix real part, yeah, B matrix real part is in diagonal minus 0.5 minus 0.3. And B matrix imaginary component, again the diagonal, which is 0.2 and 0.1. Then C dash matrix real part. Okay, so real is 15 minus 5 minus 5, 5. And C dash matrix imaginary part minus 14.8, 55, 4.8. So now we have real and imaginary parts of the matrices, and now we need to formulate this matrix. We need to arrange this matrix. So starting from left hand side, we have minus A dash real minus A dash imaginary on the left hand side. So here we have A dash real and A dash imaginary. So we need to arrange the matrices one below the other like this. So negative of A dash real, so that gives 9 minus 0.6, and here minus 9.6 and 0.2 on the LHS. Yes. And on the RHS side, we have four submatrices. Okay, so first we have BR and CR dash, the addition of them. So BR and CR dash, so their addition. So 15 minus 0.5, that gives 14.5, minus 5 plus 0, and 5 minus 0.3, so that gives 4.7. That is the one. First part is done. Second, we have BI minus CI dash. Okay, so BI minus CI dash, this minus this. So this becomes, addition of this becomes 15. This BI minus CI dash minus 5 and 0.1 minus 4.8, so that is 4.9. So first two rows completed. Now for next two rows, we have BI plus CI dash. So BI plus CI dash. Okay, so their addition, simple addition. So here we have 5 and 5 simple thing first, then 0.2 minus 14.8. So that gives minus 14.6, and 0.1 minus 4.8. So that gives minus 4.7. Okay, then we have lastly CR dash minus BR. So CR dash minus BR. So we need to subtract this from this. Okay, CR dash minus BR. 15 minus 0.5. So that is 15.5. Yeah, minus 5 and um, yeah, 5 minus 0.3. So that is 5.3. And here we have Vn real and Vn imaginary. So real part first, Vn stands for all the bus voltages except the substation. So this matrix will be like V2 real, V3 real, then V2 imaginary, V3 imaginary. So that part is V2 real, V3 real, V2 imaginary, and V3 imaginary. Right. So here we have got a system of linear equations, and here the only unknown is the voltages V2 and V3, their real part and imaginary parts. So we can solve this equation. This equation is in the form of what we have already seen in a typical linear system of equation, like A x plus B. Sorry, AX equal to B. So one way to solve is take that A matrix inverse into B, and this we have seen this is not a computationally efficient way to do that for a very large scale system. So what we will do is we have got this equation. We will define this as B matrix and this as that A matrix in MATLAB, and we will solve this system of equation in MATLAB by this method first. And the second method that we have seen earlier is without taking the inverse of A matrix, we can actually solve it. So that method is by LU decomposition and backward and forward substitution. So in MATLAB, that can be obtained as like this. So the MATLAB command for that is A backslash B. So let us do both the ways MATLAB, and in MATLAB, let us see how much time the MATLAB takes to compute the same thing by two different approaches. Okay, so X in this case is this unknown quantity over here, the voltages. So let us define first B matrix and A matrix and then do this calculation. So let's go ahead. So let's define B matrix first as 9 minus 0.6, 9 minus 0.6 minus 9.6 and 0.2. Sorry. So that is the B vector. Similarly, the A matrix is 14.5 minus 5, 15 minus 5, first row over. In second row, we have 5, 4.7. Okay, then third row, 14.6, 5, 15.5 minus 5. And in fourth row, we have 5 minus 5 minus 4.7 minus 5 and 5.3. Okay. Okay, so this is the A matrix. And in MATLAB, we have to do the calculation both the ways, the first way and the second way. So let us define that V as first way is taking the inverse of A matrix and multiplying that with the B vector. So this is the first way. So in MATLAB, the time taken to execute this command can be calculated by using the command tick tock. So write the tick at the beginning of the code and write the tock at the end of the code. So it gives basically the time of executing that command. So if you just run it, you can see the elapsed time is 0.2 second. Okay, let us print what is the voltage equation we are getting. So this is the voltage equation. Now let us do it another way. Instead of doing it, calculating inverse, let us do by our LU decomposition and back substitution in this method. And the time taken is, you can see 0.005 344 second. And the answer that we got, you can compare this with the previous answer. It is one and the same. So the first two things indicate real part of the V and V2 and V3. And the second the last two indicates the imaginary parts. So you can see the voltages are approximately 0.95 and 0.93 approximately. So there is a voltage drop. It is not 1 per unit. So that is obvious kind of thing. And we can compare the time taken. So how much reduction in time. So in one case we have 0.2 and in other case we have 0.005. So let us just compare those timings. So how much time we have saved. So basically this subtracted from this time. Okay. So that gives approximately 0.2 second. Okay, so 0.2 second is nothing because this is just a three bus system. But when it comes to thousands of buses, then and we need to solve the load group of several number of times, then this thing matters. Okay, so we don't prefer in power system taking the inverse of a matrix and solve for unknowns, but we do it by LU decomposition method as discussed in the earlier class. So this was one of the simplest method by which we can obtain we can obtain a linearized form of load flow equation and solve it in just one simple iteration. There is no need to perform any other iteration. Okay, in just one iteration, we got the answer. So you can go ahead and compare this with actual backward forward sweep load flow or any other method that we have covered in the class, and just compare with the help of linearization how much accuracy we are getting as compared to the backward forward sweep or any other load flow method, which is the accurate method. So that you can go ahead and do that kind of comparison. Okay, so we will stop here.